This content is brought to you by Dr. Red's Virtual Labs. Sign up for free and start learning by doing.
Most student exercises focus on simple reactions with easy analytical solutions. Today, we explore just a little more advanced cases involving multiple reactions occurring simultaneously in a reactor. The core message is this: even complex systems follow the same rules as simple ones. We just need a little more powerful solution methods for the equations. Take oligomer degradation as an example. Each reaction that breaks a bond creates new molecules. These can degrade further, adding to the complexity of our task. What would a kinetic model for this system look like? And how can we use it to simulate the behavior of the ideal reactors? Let's find out. We assume all reactions are first order and each bond has an equal chance to break. For the dimer, M2, the rate equation is particularly simple. Now consider a 5-unit oligomer, M5. It's symmetric, so there are 2 bonds in the second position from the chain end. Both have the same probability to break, therefore the rate constant doubles. Note that this is not a stoichiometric coefficient. Next, let's proceed to write rate equations and rates of formation for each oligomer in this system. The pentamer, M5, degrades 2 ways. Its formation rate is the sum of these rates. The value is negative because M5 is consumed. The tetramer, M4, also degrades 2 ways. Reaction 4 is half as likely as reaction 3 due to bond locations. To find M4's formation rate, we observe it's formed in 1 reaction and consumed in 2. The trimer, M3, is formed in 2 reactions and consumed in 1. 3 reactions produce the dimer, M2. Reaction 4 yields 2 M2 molecules, so we include the stoichiometric coefficient 2 in the rate of formation. The monomer, M, is stable. A single monomer is formed in reactions 1, 3, and 5, whereas 2 monomers are formed in reaction 6. That's quite many equations. We observe that each rate equation is just a constant factor times a concentration. This type of a system is ideal for matrix representation. We organize the rate constants in matrix K and the concentrations in column vector C. The use of boldface is to underline that these are matrices or vectors. Our system has 6 reactions and 5 chemical species, which results in matrix K having dimensions of 6 rows by 5 columns. Each row corresponds to a specific reaction. For example, to compute the rate of reaction 1, we perform a dot product between the first row of matrix K and the column vector C. Likewise, the rate of reaction 5 is calculated in a similar manner. In the mass balance equations, we're actually interested in the rates of formation, which are derived from the reaction rates by multiplying with the stoichiometric coefficients. This can also be elegantly achieved by matrix multiplication. While it may seem that these matrices take a lot of space, the payoff comes during numerical solution. Writing out the coefficient matrices just once keeps the code remarkably compact and clean. For a batch reactor with constant density, the mass balance equations produce a system of 5 coupled ordinary differential equations, ODEs. These can be conveniently represented in matrix notation for easy numerical integration. In a plug-flow reactor, the steady-state mass balance equations can be integrated to provide internal concentration profiles as a function of the spacetime. In a continuous stirred tank reactor, CSTR, the situation is somewhat different. Here, the steady-state mass balance consists of algebraic equations rather than ODEs, but these too can be written in matrix form. Now, let's turn to the Python implementation of the batch reactor model. If you're working with Matlab, you'll find the code structure almost identical. After importing the necessary numerical libraries, we set the rate constant to 0.003 per second and initialize the rate constant matrix K as well as the stoichiometric coefficient matrix nu. In the derivative function, we calculate the rate of concentration changes at each time step. The use of matrix operations makes this function both short and easy to read. In Python, matrix multiplication is denoted by the @ sign. The integrator needs to know where to start from. The initial conditions are set in column vector C0. The time steps for numerical integration are defined in vector T-span. generated by the linspace function to create equally spaced values ranging from 0 to 80 minutes. Lastly, the ODINT function handles the numerical integration. The output is stored in matrix C. Before running the simulation, let's run an experiment in the virtual lab to understand what to expect from the simulation. In this scenario, the reactor is charged with 0.4 moles per liter of compound M5 and runs for 80 minutes. We want to save the result of the experiment. All data can be exported from the virtual lab in either Excel or Matlab formats. Here's the batch reactor data. Initially, only the largest oligomer is consumed, and concentrations of all the smaller molecules increase. Soon, the degradation rates of M4 and M3 exceed rates of production, and concentrations start to decline. Eventually, everything will be converted to the monomer M. Let's look at the simulation result. The model prediction fits very well to the virtual experiment, just as it should be. As already mentioned, calculating the steady state of a CSTR involves solving a set of algebraic equations. Here we use the root function from Python Scientific Computing Library. The mass balance equations are given in the wittily named function mass balance function. Note how the left and right side are written just as you'd write with pen and paper. Again, we do matrix multiplication by using the AT sign. The feed composition is defined in vector C in. The spacetime is 50 minutes. The solver needs an initial guess for the concentrations. These values are obviously wrong, but not totally unreasonable. The output of iteration is stored in an object called result. The last row of the code extracts the exit concentrations from the object's attribute X by using the dot notation. We can add a few lines of code to get a nicely formatted output. According to the calculation, there is still some of the higher oligomers left with 50 minutes spacetime. Let's confirm the calculation result with a quick experiment in the virtual laboratory. We use spacetime of 50 minutes and set the feed concentration of M5 to 0.4 moles per liter. It is important to operate the CSTR until it reaches the steady state. Let's hope 10 hours will do the trick. We run the experiment and download the data when it finishes. Dr. Red's Virtual Labs provides the option to run experiments in real-time mode. Here it would mean a 10-hour-long experiment, so we are happy to operate the reactor in lightning mode. Ah, look at that. Our calculations and experimental results are in harmony again. But what's this? A bit of noise in the concentration data? That's normal in all experimental work in chemical engineering. We'll just have to cope somehow, won't we? The oligomer degradation system was fairly linear. How do we handle reversible reactions and second-order reactions? Here, our target might be to produce compound P, but it reversibly decomposes to R. We begin by rewriting the reversible reaction as two irreversible reactions. If all steps are elementary reactions, writing the rate equations becomes straightforward. Observe the second-order term in reaction 3. The rates of formation are yet again derived from reaction rates, utilizing stoichiometric coefficients. Once more, matrix operations come to our aid. Let's determine the concentration profiles in a plug-flow reactor under steady-state conditions. The approach is basically the same as with the previous batch reactor. We assign values to the rate constants and formulate the matrix of stoichiometric coefficients. Due to the second-order term in rate equation 3, we compute the column vector of reaction rates somewhat manually in the derivative function. Again, time derivatives are easily calculated via matrix multiplication. Regarding the numerical integration, the initial concentrations in vector C0 represent the feed. The integration time span ranges from 0 to the selected spacetime, tau naught. Once more, we invoke ODE-int for the integration. Plotting concentrations against time gives us the reactor's internal concentration profiles. 0 residence time marks the reactor's inlet, and 15 minutes its outlet. Reactant A is fully consumed. It appears we've selected an overly large spacetime, given that the product partially degrades to impurity R near the reactor's end. Optimal spacetime naturally depends on the desired conversion of A and product purity, often influenced by downstream separation costs. Let's corroborate the computational results in the virtual lab. Set the spacetime at 15 minutes and feed concentration to 2 moles per liter. In an ideal plug-flow reactor, the runtime should exceed the spacetime just slightly, given the absence of axial mixing. The result of the PFR experiment is the exit concentration as a function of runtime. Notice the abrupt shift in exit concentrations when time equals the spacetime, marking the moment the reaction mixture has traveled through the reactor. As anticipated, experimental results affirm our calculations are spot on. That concludes our discussion for now. Hopefully, you're now at ease with these more complex systems, which, when you get down to it, are just like the simpler ones.